Chapter 6, Section 3, Addition, Subtraction, and Least Common Denominators. Well, what we're going to do with rational expressions again is, which are fractional expressions. Rational means a ratio or something I can make a fraction out of. Well, when we get into that, we talked about multiplying and dividing last sections, and now we're going to talk about addition and subtraction, which is usually more difficult when we get into having different denominators because we have to have the same denominator to be able to add the numerators, or in the case of subtraction, subtract. So basically they're going to start with those facts and summary of that information, which I think we all know. And like if we have fractions like 2/7 plus 3/7, because they're really the same size pieces, if I think about pizza, because I like to eat pizza, is if I have it split into sevenths, if I have 2 pieces and 3 pieces that are the same size, I end up with 5 of those same size pieces. Well, that only works if this size of the piece is the same, or the denominator, the divisor of the division, right? A lot of different ways to say that is exactly the same. Well, and that's really the rule, is once these denominators are the same, how do I perform that addition? Is I just add the numerators over that same denominator. When we get into more complex expressions and doing that stuff, I would go right back to this. This is a strategy called solving a simpler problem. If you're not sure what to do with these situations, add 2/5 plus 1/5, and what would you get, right? Is it really doing a simple problem? You think about, well, how do I get 3/5? I don't get 3/10. I don't add the denominators, all that kind of stuff, which I see those kinds of errors occur once we start dealing with just variables. But the rules are that way, so when the denominators are always already the same, so in this expression like example A, 4 over A plus 3 plus A all over A, I can just add the numerators and those kinds of things. Now, and in these examples, first of all, that's all they're really trying to show you, but later on we're going to have some expressions like this, and there may be some opportunity to simplify to do some things too, but we're going to run into that later. So they set this up here, and even this one here, like C, I'd say, well, yeah, that's easy to factor. That's difference of squares. That's x plus 3 times the quantity, or the other binomial of x plus 3, and so on both of these. But there's no real advantage to doing that. When I have the same denominator, then what I do, just like in this example down here, I just add their numerators, right? Like C here. And then I get this result. Well, x minus 5 plus 2 ends up to be x minus 3. Now it's important to deal with, hey, is this fraction in simplest form? How do I do that? Well, that's section 2, is that I make sure that I factor everything completely, and then I can write the fractions where I have a numerator over numerator that's the same. I end up with fractions equal to 1, right? Which allows me to simplify fractions. The definition of a fraction in simplest form is that the greatest common factor, or the factor that are common between the numerator and denominator, can only be as big as 1. And in this case, 1 is a factor of 1, right? And what are the factors of x plus 3? Well, it'd be 1 and this quantity x plus 3. So the greatest common factor between this numerator and this denominator is 1. That's the definition of simplest form. Well, how do I get rid of factors that are bigger than 1 or other than 1? Well, I match them up to make fractions equal to 1, which is like multiplying by 1, the identity of multiplication, and those things kind of go away in a sense, as I end up with a simplified fraction. So good point here, and why I kind of jumped to this example is that, hey, you can do the addition correctly, but you still have to make sure you check. You can end up with a sum or a difference when we get into subtraction that may not be in simplest form, so make sure you check that. Well, subtraction is very similar. If I have the same denominator and I'm subtracting these two fractions, then I just subtract the numerators. And there's a caution here. It says a fraction bar under the numerator is a grouping symbol, and this is really true. So you can't necessarily just treat these subtractions a certain way, and they really didn't caution you in the beginning with addition, because addition has the associative property. I can group addition any way I want, even though it truly is true that fraction bars really create a grouping as if there's a parentheses around them. It's no big deal with addition because the associative property works on addition. It does not work on subtraction, so that's why we need to deal with that here. Let's look at these examples. Example A here, I got 3x all over x plus 2 minus this fractional expression x minus 5 over x plus 2. Well, they have the same denominator, so I can just subtract the numerators. Very common error though, you got to subtract the entire numerator here. In other words, this is like there's a grouping symbol around this. It's like taking the opposite of what's in this parentheses, and I end up with a negative x plus 5, the opposite of negative 5. And now it's in terms, I'd say plus a negative x, and then I don't worry about order, but I can combine these two like terms here, and I get 2x plus 5 all over x plus 2. Well, then I'd have to check this again and make sure that there's is in simplest form. And again, our strategies on factoring is look for the easiest factoring first, which is a common factor for the terms. There's a 2 and an x and a 5 and a 1 here. No common terms. Same thing. These are both prime in a sense. And then at that point, hey, I have binomial. The only thing I can factor for binomials is difference of squares, and you should look for that one first because that's easier to factor. And then we have sum of cubes and differences of cubes. So none of those things are there that we can basically say we can factor, and these are no basically values that I can create into a 1. So this is in simplest form. Or in other words, the numerator and denominator have a GCF of 1, greatest common factor. Definition of simplest form. And so on. But really what you got to be careful about is subtracting groups. See a lot of errors around that. And in example B, they do the actual subtraction. They end up with a trinomial. They factor that trinomial. Because that's, first I look for common factors again. There's no common factors in any of these terms, or all these terms. So you can use grouping or reverse FOIL. You know, I need factors of negative 12 that will add up to a negative 1. And so that would be a negative 4 and 3 and x for x squared. So I factor this. Now I have a common factor of x minus 4 over x minus 4. I can write that as a fraction like this, which is equal to 1. The shortcut is to cross these two things out basically, and you really probably should put a 1 there too. That's pretty good practice. Say, hey, I'm basically changing these things to 1 over 1, because I might need to know that there's a 1 there, but I end up with basically this simplifies to x plus 3. Now what they're setting up in this next portion here is finding least common multiples and least common denominators, because that, remember when we were adding fractions, if I had thirds plus halves, I have to find a common denominator, which would be 6, and then I can change those fractions by multiplying by 1. And probably I think the confusing part is that we get so used to simplifying fractions, when we're trying to do addition and subtraction with unlike denominators, we're actually going to put in 1s, basically special 1s, to make sure that my denominator can be the same for both fractions. And then they go back to basically math, and they said when we did arithmetic, recall that if you add 1/12 to 7/30, first we identify the smallest number that contains both 12 and 30 as factors. In other words, multiples of 12 and multiples of 30, and we want the least one of that, or least common multiple. Well, you could do that, I mean, just to remind you what multiples are. Multiples of 12 are 0, 12, 24, 36, 48, right? I'm just adding another 12, right? Or another number higher times 12. Factors of 30 are 0, excuse me, but we're not going to use zeros. And 30, 60, 90, and so on. Now I could go, well, 5 times 12 is 60. There's my common multiples. That's the first one that becomes common, and I could say I need to write these new fractions as 60ths, and so on. Kind of doing old school, probably the things we were introduced to. And then what they're going to do here is basically we can find least common multiples by using prime factoring, which we've done a lot of. And this is they're showing the prime factorization of 12 and 30, which 12 is 2 times 2 times 3, 30 is 2 times 3 times 5. Now to find the LCM, we take all factors, all prime factors for both, and only take the common ones once, or where they overlap we just use once. And they kind of show this sorting of this then. So I have a 2, 2, 3 and a 2, 3, 5. Well, if I write that out, I got a 2, 2, 3, right, for 12, and then this other 5. There's a crossover between these two 2's and the 3's here. So they don't write those again. They basically kind of write it on top of that. And if I multiply that result of that overlap of prime factors, it'll give me the LCM. Because 2 times 2 times 3 times 5 is 60. So we can rewrite these fractions as something over 60. And how did I get 1/12 to 60, or 12 goes to 60? I have to multiply by 5. So I take the denominator times 5, so I have to take the numerator times 5, which is multiplying by 1 in a special way. But also I'm proving that these fractions are both equal. They're just different versions of the same value on a number line. And so that basically first we got to find that least common multiple in this case. And that's what they're stepping us through here. So we find that the prime factorization of 2, 3, and 5 is used the greatest number of times that it appears in either of the individual factorizations. The factor of the 2 occurs twice, the factors of 3 and 5 occur once. Okay, so we end up with 2 times 2 times 5, which is 6 times 5, or 60. Okay, or 30, excuse me. I'm breaking into different problems here, I'm sorry. Well, this box kind of tells us a procedural way to do that. You can memorize this and stuff like that, but I think if you understand what multiple means, or denominator means, what's common means that it's in both, right? And we want the least of those, because there's there's an infinity of common multiples for any number. We want the smallest one of that. So they tell us this practice, or how this will work. You can write the prime factorization of each denominator. 2, select one of the factorizations and expect it to see if it's completely contained in the other factorization. In other words, is the other factorization a multiple of that other one? If it does, it represents the LCM of the denominators. If it does not, multiply that factorization by any factors of the other denominator that it lacks. And the final product, the LCM of the denominators. Now that's a whole mouthful of stuff. What I like to do a lot of times, and then we're going to show how these stack up, and I do something called Venn diagramming, which I'm not set up here to draw very well, but we'll talk about it when we go through these next ones. So example 3, they want to find the least common denominator between these two fractions. So we're talking about denominators. So we want least common multiples of these two denominators. Well, they prime factor 36x squared, and they get these factors here in the red. We got 2 squared times 3 squared times x squared if I wanted to put exponents still on it. And here I got the prime factorization of 24x, which is 2 to the third times 3 times x. So there's our prime factorizations. And then they stack these things up and basically represent all values, and anything that's common or shared between those two, I only represent that once. So that's what they're showing us here. And then when I only represent these, like the 2 occurs in both the 24x and the 36x squared. This, another 2 occurs, the other 3, and then there's a 3 here on this one, but it doesn't occur here. That's what these little lines are indicating. Hey, this one occurs in both. This one doesn't, and this one only occurs in the 24x. So what we take is what is written here. Instead of representing, this 2 twice as 2 squared, I only have to represent it once if it occurs in both, right? So we end up, and then you multiply basically with those commons represented in an overlap way. We multiply that out and we'll get 72x squared in this case, which is the LCM, or LCD really, because we're talking about denominators, and of those fractions of 72x squared. Okay? Now they're kind of jumping back to another problem here. So now let's add 1/12 and 1/7/30. Well, what we do is find that LCD between these two numbers here, or these two denominators of 12 and 30, and they go through that prime factorization, and we find out the LCD is 60. Well, that's what they're showing us here. Now, how do I change this 12ths into 60ths? Well, I look at what's in the denominator now, which is 12, or I like using my prime factorization. I say, hey, what part is missing out of the prime factorization that will multiply to be 60? Well, I got a 2, 2, and a 3 here. What's missing is a 5. So I need to put a 5 in the denominator, but I can only do one kind of multiplication that doesn't change the value of anything, and that's multiplying by 1. If I put a 5 in this denominator, I have to put a 5 in this numerator right here, which then is equal to 1, but I end up with 5 over 60. And I basically, with this math right here shown this way, or my work, I can say I've proven that 5 over 60 lies exactly in the same position on a number line as 1 over 12. Because to get from here to here, you multiply by 1. In this case, I multiplied by 5 over 5. Well, same thing with this 7/30. I have a 2, 3, 5, a 2, 3, and a 5 used up. I still need a 2, so I'm going to multiply by 2 over 2, and I'll end up that this thing I already know multiplies to be 60, and then I take 7 times 2, I get 14/60. So now I'm back to the beginning. How do we add fractions with the same denominator? So I find the LCD, which indicates what I need to do. If you do it with prime factorization, I will be able to pick out what I need to multiply by to get my new fraction with the same denominator. And once we have the same denominator, you just add the numerators. So same thing if we have variables. So they're going to take an example like this one, 5 over 36x squared and 7 over 24x, and they're going to say, what happens if I add these things? Well, I need to prime factor them, find out what my LCD is, and in this case, we already did this, which is through the prime factorizations, we found out it is 72x squared. But I wouldn't write that down really yet. I'd probably leave this prime factor, and we'll talk about that in a little bit too, is that when I simplify fractions, if they're prime factored, I'm going to be able to hopefully pre-simplify this as I'm working with this. So let's look at this part here. Because after the addition, what do I need to do? I need to check to make sure we're in simplest form. Well, in this case, to get this 5 over 36x squared, we need to find out I need another 2 to multiply by, because that'll give me 72x squared. Well, I multiply by 2 over 2. To get this denominator of this 7 over 24x right, I need to multiply the denominator by 3 times x. And then I make sure that I'm only multiplying by 1. So now I end up with 10 over 72x squared, and I end up with 7 times 3 times x, which is 21x over 72x squared. And then when I have the same denominators, I add the numerators, and I end up with 21x plus 10 all over 72x squared. Kind of lots of steps, and it looks like a lot of complexity, but it's really the same process. So really try to focus in on, why am I doing this? I need to get a common denominator and do those kinds of things, right? To do that, and the process is what's important, and then we'll get the math and how to work with prime factorization, that kind of stuff, to do those kinds of things, which is going to be important in a lot of ways when we add and subtract. Now, some of the problems you're going to do in this section is just find LCMs, least common multiples. So we practice that between these two. I'd prime factor that. I'd get 3 times 5a times a, and 35b is 5 times 7 times b. And then to find this LCM, I just basically rewrite this all factors seen with the common ones only represented once, or kind of overlap them in a sense. And I end up with this new multiplication, which would end up to be 105 AB. So remember that, even though they're variables, they're not common unless they're exactly the same variable. So the LCM is right here, is a multiplication of those prime factors. Example B does the same thing. Lot of x's, lot of y's. Make sure that you get your exponents right by counting how many times they're factors. And the same thing here too, is that if I want to find the LCM between x squared plus 5x minus 6, can I factor that? Isn't that what we're doing up here, is we're prime factoring? Well, prime factor this trinomial. Remember the process. I got 3 terms. I look to see if the first term something squared. If the last term something squared, then I possibly have a perfect square trinomial. Well, 6 is not something perfect squared, or negative anything isn't. So I use reverse FOIL or grouping, and I end up with this factorization. The process we go through is, well, first common factors. I forgot that. Do I have any common factors for these terms? No. I have a 2-term or a binomial. What can I look for? I can look for difference of squares, or sum of cubes, or difference of cubes. It's the only thing I know how to factor so far. So, and look for difference of squares first, always. Well, this one's pretty simple one, x squared minus 1 squared in a sense, right? So you end up with these 2 binomials factored into x minus 1 times the binomial x plus 1. So when I list these prime factors, these are really prime factors, just like for 10, 2 times 5, or 2 and 5 are prime factors. So are these. These are prime factors. I can't break these into other factors at all, so they're prime, other than 1 times them. Well, I write all these factors and I overlaps. I just write once and I end up with this new multiplication, which is my LCM. And I would leave it this way. I would not multiply that out. You're going to just take a lot of chances for errors where this will suffice for a answer. And that kind of answer shows me, hey, you know how to factor these trinomials and binomials and that kind of stuff, and you also understand what a least common multiple is. Well, example 5 is, hey, this works not just for two things. We could have three things, and you got to remember that the common ones are represented for each line that comes off of each number right here. So they kind of color coded this. They said, well, 12x, let's let that be up here, this red stuff, and I got 2 times 2 times 3 times x. The 16y will be represented by this blue line, which is 2, 2, 2, 2, y. 4 2's and a y. Okay. Notice that we already had a 2 up there from the first term. 8xyz is this black line. Well, we have a 2, 2, there's no 3, there's an x, and there's another 2, and no other 2's, but there is a y, and there's a z. If I sort this out this way, my LCM for all three of these is this multiplied out, or 48xyz. And then they go on to more complex factoring, really. And just remember what the principles are, and hopefully you remember most of the things we've done for factoring. Talk to you later.